Hello, and welcome back for section 6.2. We're going to apply the normal distribution that we just learned about in lesson 6.1. So let's see how we can tie in this normal distribution with regular context of other situations. So it says some doctors believe that a person can lose 5 pounds on the average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. Let X equal the amount of weight loss in pounds by a person in a month. Use a standard deviation of 2 pounds. So let's suppose that the person lost 3 pounds in a month. Then we're going to calculate the z-score as 3 subtracting the mean divided by the standard deviation of 2. That would be a -1. So if we used, if we drew this as where, if we did, this is the weight loss, and we drew the empirical curve, then our mean would be at 5. The first standard deviation would be at 3, 1, and then a -2, and then 7, 9, and 11. Okay. And if we use z-scores, then the mean would be at 0, and this would be a -1, which corresponds to the person losing 3 pounds, which corresponds to a z-score of a -1, a -2, a -3, a +1, a +2, and a +3. There you go, such as that. So we could look and see what is the probability that, so if, because this z-score is a -1 and it corresponds to this person's weight loss of 3, if we wanted to see what is the probability that the person actually lost less than 3 pounds, that would be this way. Less than 3 pounds is the same. It should be equivalent to see if the probability that z is less than a -1. So this one we already know from lesson 6.1 that if z is normally distributed with 0 and 1, we can find out this probability here. So let's share our screen here. And we can say, it says 0, 1, and we'll put in a -1. So it's 0.1587. So what if we said, if the person weighing 3 pounds or losing 3 pounds is equivalent to a z-score of a -1, maybe we could just put in the mean of the situation, which is 5, and the standard deviation of the situation, which is 2, and say, what is the probability that the person lost fewer than 3 pounds? And look at, we have the exact same probability. And that is because instead of taking each particular situation and turning it into a z-score and using the normal distribution, we can just use if we know that our data is normally distributed, which it says that it is, then we can use that distribution and say X is then normally distributed, in this case with a mean of 5 and a standard deviation of 2. I wrote it right here. And these come out to be the same thing. So instead of just using normal distribution of 0 and 1, we're now going to use the normal distribution of the mean and the sigma of the situation. So it says, we learned earlier in the semester that an unusual observation is one that is more than 2 standard deviations above or below the mean, used as most to find the sum of these probabilities. So I want to make sure that we're understanding what it means to be unusual with the normal distribution. So if we're past 2 standard deviations this way and past 2 standard deviations this way, what does that mean? So we're going to say the probability of z being less than a -2 plus the probability of z being greater than a +2. Go ahead and copy that. But now we're going back to the z. And so a -2 here. The other one. And then it's twice that because they're identical. There's mirror images. So 0.02275, 0.02275. So 2 times 0.2275 is approximately 0.045. So almost 5%. And that is why we say that, I'm going to do the other one as well. And this one is going to be 2 and above. So you can see on this curve, on this graph now, it shows the unusualness over here and the unusualness over here. And if you add them together, it's 0.0455, which says that if our likelihood is less than 5%, then we're considered unusual outcome, which also is in agreement with being outside of the 2 standard deviations that we talked about back in chapter 3. So we're going to make sure that we keep that in mind. Let's go ahead and look at example 2. So the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that a randomly selected student scored more than 65 on the exam. So X is normally distributed with mean of 63 and standard deviation of 5. And so there is our center at 63, and we want to know the probability of being greater than 65. Remember, that's a greater than. And so I'm going to mark 65 here, and I'm just going to shade showing this is the probability that I'm looking for here. So this is what it should look like in Desmos. And this is what I'm going to put in because I want to be greater than 65. My mean is 63, my standard deviation is 5, and I should get 0.34457. So let's check it out here. And I typed it in here in the Desmos, and there it is, and just like the picture that we just drew. So if you flip your page, it says find the probability that a randomly selected student scored less than 58 on the exam. So this time I'm going to copy that. I'm going to turn off that graph. And this time we want to know less than 58. So that means I have a negative infinity up to 58. And that's what that would look like. And so on your paper, the probability of being less than 58 is 0.1587. We'll have to flip the page. So sometimes, just like we did in 6.1, we know the area or the percentage, and we want to find the X value that goes with that. And so we learned in 6.1 how to use inverse CDF when we want to find the area or the percentage under the curve. So C says find the 70th percentile. So we're going to remind ourselves that 70th percentile is when 0.7 or 70% of the data values fall below this X value right here that I just drew, and 30% is above. And so we're going to put in 63 as our mean, 5 is our standard deviation, and we want to find the X value of 0.7 being to the left because it's the 70th percentile. And that will come out to be X equal to 65.6. So I'm going to show you on my in Desmos. So in Desmos, we're going to type in inverse CDF of the normal this. And we have 63.5. And it does indeed come out to be 65.622. And letter D says find a score that meets the top 10%. The top 10% means that we want to have 10% out here. And so we want to know the X that marks that spot. Well, that also means that, remember, when we're using the inverse CDF command in Desmos, we have to do 1 minus that area. So we have to do our left-tailed area. So instead of using 1 minus 0.10 in my command, I just typed what I know is 1 minus 0.10 or 0.9. So you could do 1 minus 0.10 or 0.9. Either of those will work. And you will come up with a score of 69.4. So only 10% of students scored higher than 69.4% on the exam. Let's look at example 3. It says the golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a randomly selected golfer scored less than 65. So team average was 68. We want to know what is the probability that the golfer scored less than 65. And X is normally distributed with 68, 3. So we are going to go to Desmos. And I'm going to use and we're going to do a normal distribution. The golfing, and their mean was 68 with a standard deviation of 3. And we want to find out the probability of scoring less than a 65. Let me turn this other one on here. So there it is. You can see it in my picture. I'm just going to, it's a little bit more centered this way. So it looks like there's a 15.86% likelihood that the golfer, 15.87% likelihood that the golfer scored less than a 65. E says find the probability that a golfer scored between 66 and 70. So 66 is just below the mean and just above the mean. And so I'll share my paper here in a minute, but let's go ahead and see if we can do it with before I share my paper. So that means I'm going to copy what I've got set up here. I'm going to paste that. And we want to know between, so my minimum would be 66 and my max would be 70. And it looks like that probability is 66 to 70, and that's equal to 0.495, almost 50% of the data is between a score of 66 and 70. And then part C says, what score would a golfer need to be in the top 15%? Okay, so that means we're going to use the inverse CDF of this situation. And the top 15% means that we have to put in 1 minus 0.15 to get the correct value. And I will show you my paper before we come back and prove it. Here are the other two pictures that we validated. And so we want to know the X value that goes with the top 15%. Okay. So that would look like this. The probability of X being greater than something equals 0.15. And it looks like we came up with the answer of 71.1. So, but in reality, the score would have to be a 71, right? Or 72. We can't have a decimal score for a golf score. Let's look at it. Example 4 says, in the US, the ages 13 to 55 plus of smartphone users approximately follow a normal distribution with mean and standard deviation of 36.9 years and 13.9 years, respectively. Determine the probability that a randomly selected smartphone user is between 23 and 64.7 years old. So X is normally distributed with 36.9 and 13.9. And we want to know the probability that the user is between 23 and 64.7. And you don't have to fill out the entire curve, just kind of where the mean is. And so you get a perspective of where 23 might be, and then 64. So it's just my guess of kind of what it might look like. Okay, so we want to know that probability between 23 and 64.7. So okay, let's go. Let me go to that. Okay, so we want to know between 23 and 64.7 years. So 82.9% or 0.86% of users are between 23 and 64.7. A large proportion. Part B says find the 30th percentile and interpret it in a complete sentence. Let's go back here to our paper. 30th percentile. So 30th percentile means 30% is below. So I know that's on this half of the graph. So I want to know the probability. I want to find the X where it's the X that marks less than or equal to 0.30. And so I have to use my inverse CDF in this case. And we have 30% is the left screen and Desmos. There it is. It looks like an age of 29.6 years old. So that means that 30% of smartphone users let me share my screen so you can see what I'm writing. 30% of smartphone users are 30 years old or younger. What is the probability that the age of a randomly selected smartphone user is in this range is less than 27 years old? So the age is 23 is the whoops 36.9, sorry, 36.9 is the mean, and so less than 27 is going to be maybe here. So we're saying what is the probability that they're less than 27? So we're looking for probability. So we can just use the normal CDF, or I'm sorry, the normal distribution. And we'll put in it looks like 23.82% are less than 27 years old. And this example has 2,000 students who have been the scores on the exam have an approximate normal distribution with a mean of 81 and standard deviation of 15. Calculate the first and third quartile scores for this exam. What does this tell you? So first and third quartiles. First quartile is Q1, which is 25%. And third quartile, Q3, is a 75%. So we need to find one that's 25.25 is, we're going to call it X1 that we're looking for. So X1, the probability that X1 is less than something is equal to 25%. We want to know that. And then that's our Q1. And then the Q3 is the probability that the X3, we'll call this one X3. And we're going to just shade over that. That's all of this right here, right? Everything that's 0.75. So let's go to the mean is 81 and standard deviation 15. Okay. And we want to know we need our numbers, yeah. And then So it looks like 25% scored less than a 71. We have to round that. Remember, percentiles, we have to round to a round up. So 71 on this on the exam. And then we're going to copy that. And the other one for the Q3 is they scored a 91.1, so it has to be a 92. Okay, let's go the paper and look at the last part of this problem. It says 60% of the students earned at least what score on the exam. 60% earned at least what score? At least tells us bigger than. So we want to know what score in the exam where they scored at least 60% of the students. Okay, so that means that there's half. So I'm going to say this would maybe mark the 60%. We want to know the score that where 60% of the students scored bigger than the score. And we have a right area, so we have to tell it in Desmos 1 minus 0.6 or 0.4. Make sure that we get the right value. So let's go back to Desmos and see this here. So we're going to tell it 1 minus 0.6. So it looks like it's 78. So 60% of students scored at least a 78 on the exam. That's pretty good. So there's 2 videos to lesson 6.2. This is the last problem on this first video here. And it says, grows mandarin oranges, finds that the diameters of mandarin oranges harvested on his farm follow a normal distribution with a mean diameter of 5.85 centimeters and a standard deviation of 0.24. Find the probability that a randomly selected mandarin orange from this farm has a diameter larger than 6.0. So I'm going to just do these 3 without going to Desmos. Hopefully you've had enough practice on Desmos that you can do these. So let's just, why don't you pause it for a minute and work on this and come back and see if you can check your answer if you're the same things that I do. So I'll let you pause it there for a minute. So we are no bigger than 6. So the probability that X is larger than 6.0. So that would be this way. And that is 0.266. And then next says the middle 40% of mandarin oranges from this farm are between what and what. So middle 40% means that I got 1 minus 0.4 or 60% on the outside. And 60% divided by 2 means I've got 30% on either side. So I've got 30% left of this diameter, x1 we'll call it, and 30% to the right of this diameter. So the lower one, x1, can be found, it's a less than, right? A diameter where 30% is fewer than that. So that one, when we do the inverse, that one's lined up because we have the left tail already, and that comes out to be 5.72 centimeters. Now x2, we have to treat it a little bit different. It's probably the x2 is less than, and this is 0.3, but we have to write it as 1 minus 0.3. So it's really all the shaded version over here. And that comes out to be a diameter of 5.98. So note both of these you would use the inverse CDF. And then the last problem, find the 16th percentile and interpret it in a complete sentence. So the 16th percentile. The 16th percentile means that 16% of oranges have a diameter less than this diameter. So that one is an inverse. So just a reminder, it's an inverse CDF with a normal dist of 0.85, comma 0.24, comma 0.16, and that comes out to be a diameter of 5.61 centimeters. So that means that 16% of the oranges have a diameter of less than 5.61 centimeters. Touch me back for the short but second little piece to lesson 6.2.